Welcome to lesson number 5, last lesson of the Summer Academy, where we are looking at previous topics that we've already covered and going a little more in depth into them. So here we're going to wrap up trig functions by talking about how to graph them. We'll look at the graphs of tangent and the reciprocal functions that we talked about previously, and then we're going to find the inverses of sine, cosine, and tangent. Since we've talked a lot about inverses, and those can be quite helpful and are interesting to look at. And then we'll discuss using trig functions to model real life, which we did during in Algebra 2, but we want to kind of just make sure we fully understand all the different transformations that we can make to a sinusoidal function to help us model real life. Just one thing on trig functions: if you're feeling a little hazy or just want to make sure you are 100% set on trig functions, if you go back and you go to the Algebra 2 playlist and you watch Unit 6 videos, I think I mentioned this in the previous video, that those would be a good place to go back and kind of refresh your memory on graphing and the different transformations that we can make to sinusoidal function, because I'm going to try and move rather quickly here and assume that you have the basics down. Alright, so this is the last video that we are looking at topics that we've already covered and extending them, and the next set will contain some new topics that form the basis for our study of calculus. So that way when we go into, we start next year, we'll have a pretty clear idea of some of the tools that we're going to use in order to discover different calculus concepts. Okay, so that graph, the y values went kind of far out. So on your, if you actually included y values from -4 to +4, your graph's probably nice and skinny down in the middle. But of course, looking at cosine, right, we know that the y-intercept is at 1. It then decreases, hits the x-axis at pi/2, -1 at pi, so on and so forth. And sine intersects the x-axis at 0, right? Sine of 0 is 0. And then the y value, as we move around the unit circle, starts to increase. It reaches a maximum at pi/2, right? That's at the top of the unit circle. Then starts to decrease, eventually goes negative until it's at -1 at 3 pi/2, and then back to 0 at 2 pi. And we can go negatively as well. And in looking at these functions, we should notice that there is a similarity between the two, right? It almost seems as though the cosine function, right, seems to be just like a little step behind the sine function, right? And so we want to think about the relationship between the two, and what could we do to the cosine function in order to make it the exact same as the sine function. And so I want you to think about what change would you have to make to cosine of x so that it is exactly equal to sine of x. And we've talked about this before, that we want to translate the cosine function pi/2 units to the right. And if we do that, and this is pi/2 right here, if we do that, and if you look at your unit circle, this will be very helpful. If you look at cosine, if you were to wind it back pi/2 units, and I'll draw a quick circle here. So here is where we think about cosine values beginning, because here is where x is 0. And if instead we make cosine start down here, we find that as cosine moves along the unit circle, and as sine starting here moves along the unit circle, their values are actually the same. And so what we want to do is we want to kind of wind back the clock on cosine in order to make it exactly equivalent to sine. And what that involves us doing is, instead of using cosine of x, we use cosine of x minus pi/2. And this is kind of an introduction to how phase shift works. So the function sine of x is equal to cosine of x minus pi/2. And if you want, there's a good video on this where I kind of go into it in more detail, and you guys can discuss it if you have any more questions. And similarly, I can do the same thing to sine. So if I have a cosine function, cosine of x is going to be equivalent to a sine function phase shifted to the left. Pi over 2 units. Okay? And this is really helpful because let's say you have a sine function and you want to write it as a cosine function. Well, now all of a sudden, you just have to take your sine function, subtract pi over 2 from your whatever your current argument is, and now you can write it as a cosine function. And if you have a cosine function, you want to write it as a sine function, in other words, why we call these sinusoidal, because they can all be written as a sine function. If you have some cosine function, let's take a look at an example here. Let's say that I have, cosine of 2x plus pi, just to make it a little more interesting. And now I want to turn it into a sine function. Notice here that the value of x, right, that's my original argument for cosine, and now I just have to add on pi over 2. So this will be exactly equal to a sine function with the same argument, 2x plus pi, but then with another pi over 2 added on at the end. And of course I can combine like terms here, right? Pi plus pi over 2, I can combine that and write that as 3 pi over 2. Okay? And so now I can translate between a cosine or a sine function by making a simple phase shift either to the left or to the right. And these are important and helpful to remember because it allows you to manipulate and work back and forth fairly easily. Okay, so we've graphed sine and cosine, and you should feel pretty comfortable with manipulating those. And now let's try graphing the tangent. So go ahead and try this on your own. If you need to make a table, that's perfectly fine. And if you want to challenge yourself and kind of just go through it in your head, I encourage you to do that as well. And then once you're done, you can, if you feel really confident about it, you could check your work using Wolfram Alpha or a graphing calculator, or you can watch and we'll kind of go through it in a little more detail. Okay, if you decide to make a table, don't feel as though you're doing it really inefficiently. It will take a little longer, but it's a good practice to have because whenever you meet a function and you're a little unsure about how to graph it, it's always good to organize your thoughts by making a table of input and output values. So let's go ahead and do that just to get started. Okay. And I'm just going to do this for a couple of values and kind of see where the plot is going. So let's just start off when we have 0 in the argument. So tangent of 0. Tangent is, of course, the sine over the cosine, which in this case is going to be 0 over 1, which is 0. So we have an x-intercept right there. Alright, and we can move slowly around, so let's take a look at, let's do pi over 4 first. Right, and the reason I'm doing pi over 4 first is pi over 4 is right in the middle between 0 and pi over 2, and so I'm going to see where that is and then kind of go pi over 3 and pi over 6 in between them. So at pi over 4, the tangent is 1, and that's kind of another reason I picked that. It's nice and easy. I know what tangent of pi over 4 is. So we'll go ahead and plot that point. And now we can take a look at pi over 3 and pi over 6 because those are going to be on either side of pi over 4. And so let's go ahead and look at pi over 6 first. And the tangent at pi over 6 is going to be 1 over square root of 3. Or another way of writing that is square root of 3 over 3. And if you go and you can use Wolfram Alpha or a calculator and just type in tangent of pi over 6, use pi for pi, and it will tell you that it's about 0.577 or 0.58. And that will help you give a nice approximation, 0.58, let's call it. Okay. So it's a little more than halfway. And do the best we can. And now we can try pi over 3. And you know that pi over 3, the tangent of pi over 3 is root 3, which is, let's call it 1.7. 1.73, I guess, if you want to be really nitpicky. And yeah, doing the best I can here, but you get the basic idea, right? And this should make sense because as we rotate around the unit circle, we notice that the slope of the terminal side of these angles are getting steeper, and so the tangent should be increasing because the tangent is the slope. But now notice what happens when we get to pi over 2. Okay? If you were to try and find the tangent of pi over 2, you will end up with 1 over 0, which is, of course, undefined. Right? It's impossible for us to define the tangent at pi over 2, meaning that pi over 2 is not in the domain. You cannot have an x value of pi over 2 because that makes your function undefined. And so as we've talked about previously, this is what's called an asymptote. And more specifically, a vertical asymptote, right? We're never going to be able to have an x value at pi over 2. And so because of that, we want to make sure that in our graph, we are detailing that there will never be a point at pi over 2. And so now we've got to think about what's happening as we get closer and closer to this asymptote of pi over 2, and remembering that the tangent is the slope, the sine over the cosine, and we look at angles that are getting closer and closer to pi over 2 radians, we notice that this terminal side is getting steeper and steeper, right? Now, the steeper the line, the bigger the slope, and so as we get closer and closer to pi over 2, the bigger the value of tangent is going to be, and so we're going to have a value that is approaching positive infinity. And so it will look something like that. But on the other side of pi over 2, right, we're going to be able to continue graphing the tangent, and let's think about where we'll be able to keep graphing the tangent until. So where will we have all of these undefined pieces? Well, after we move past this perfectly vertical line, we're good to go, right? There's more tangent values that we can compute, right? These all have negative slopes, and so tangent will be, of course, negative here. And we get to pi, right, then we're going to have a tangent of 0, and that's perfectly fine as well, right? And so what we want to understand is that the next time we have an undefined value is going to be at 3 pi over 2. Okay, 3 pi over 2 will also have an undefined tangent. And so in between pi over 2 and 3 pi over 2, we'll be able to graph the values of tangent. And so we can go through and we can sort of know that at pi it's going to be 0. Right? And nowhere else is it going to be 0, and let's just think about what it is as it approaches pi over 2 from the right-hand side. Well, we're going to be right here on our unit circle. This line right here has a very steep but negative slope, right? As opposed to being right here where it's very steep and positive, here it's very steep and negative. Okay? And so we know that it's going to be getting closer and closer to negative infinity right past pi over 2 on the right-hand side. And then as we move closer to pi, right, 2 pi over 3, here we're going to have negative square root of 3 as our slope, right? So remember, negative square root of 3 is going to be about negative 1.7, somewhere right there, right? And then at 3 pi over 4, we're going to have a slope of negative 1. And at 5 pi over 6, really close to pi, we're going to have a slope of negative 1 over root 3, which we found. And what is that, 0.58? Somewhere around there. And so now we can sketch the graph to the right of pi over 2 here. It's going to be very close to negative infinity, and then it's going to drop down and intersect 0, the x-axis at pi. And you might be able to imagine, right, what's going to happen as I move past pi closer to 3 pi over 2, and we think about our unit circle. Well, as we move past pi, right, we're going to have slopes that are positive again, but they're going to be, at first shallow, and then they're going to get steeper and steeper until 3 pi over 2, where it's undefined. And think about right before 3 pi over 2, these tangent lines are very steep and positive, and so they're going to be approaching positive infinity. And we don't really have to plot any points anymore. We kind of just know the basic drill at this point, right? And so now that you have this idea, you can just keep rotating around the unit circle and thinking about, okay, where is it going to be undefined? And we notice that if we keep going past 3 pi over 2, it's fine for another pi radians, another half turn, until we get 1 full turn and a quarter, right? Or a quarter past 2 pi, or 5 pi over 2. And so that will be my next asymptote. Right there. Okay, and so I encourage you to go ahead and finish this out. I'll have it finished for you in about 5 seconds or so, and we'll discuss the domain and the range of tangent. Alright, so here's the finished graph, and hopefully you were able to get the rest of it on your own. The key here to just remember is, tangent is the slope of the terminal side, the sine over the cosine, and so long as you are able to kind of picture your unit circle or have it handy, you will be able to kind of construct this. But it's good to have the image of tangent kind of always with you and understand that it has these asymptotes, these values where it is undefined. So in thinking about its domain, let's just look at this first section here, right? It's defined for values in between negative pi over 2 and positive pi over 2, but not including, right? That's why I have these rounded brackets, because at negative pi over 2 and at pi over 2, it is not defined. And then it's also defined on the other side, right, between pi over 2 and 3 pi over 2, but not including. And so what you would want to say is, you're never going to actually be asked to write out the whole domain. You might be asked to say in between, maybe 0 and 2 pi, where is it undefined? And so there you could say, look, it's undefined at pi over 2 and 3 pi over 2. And that's the real key to keep in mind. Also remember that, we could shift this, we could give it a phase shift, x plus pi over 2, and that would shift everything pi over 2 units, or x minus pi over 2. That would shift everything pi over 2 units to the right, and so that would shift the asymptotes as well. So that's a good thing to remember, right? If you have a tangent function which is phase shifted, you always want to think about the basic function, tangent, and then think about what would a phase shift do. So if you phase shifted to the right, then you'd say, okay, well now my asymptotes occur at pi and 2 pi and so on and so forth. Okay? The range is pretty simple. It can be anything from negative infinity to positive infinity, and of course we keep the rounded brackets there because we can't actually get to positive or negative infinity. Alright, so that was kind of a lot, but this is going to be very helpful because a lot of trig functions have vertical asymptotes because of the nature of there being a cosine and a sine value where there is 0, and so when you divide by 0, you're going to get an undefined value. Okay, so now looking at cosecant, secant, and cotangent, and these of course are just the reciprocal functions, so they'll be pretty easy to graph. I'm going to graph them all on one xy axis. If you are one of those people who is super neat and color coordinates and whatnot, I think that's a great idea. You can do the same to save space. I'm thinking of Michael Pineda, for example. If you are a little messier and you're worried that you're just going to do this all in pencil and you'll have no idea which is which, then maybe go 3 separate graphs. I'm not going to call anyone out specifically. So do what's best for you, but we're going to move through these rather quickly. I encourage you to try these first on your own, or at least think about them first on your own. So think about the values of cosecant as you rotate around the unit circle, and think about what that will mean for your graph. And then go ahead and press play or check your answers on Wolfram Alpha. Okay, let's start with cosecant. And the important thing to remember about cosecant is that it is the reciprocal of sine. So we can write cosecant as 1 over the sine. And so as we rotate around our unit circle, what we're doing to compute the cosecant is the reciprocal of sine, 1 over sine. So if I begin at 0, cosecant of 0, the sign here is 0. So 1 over 0, that's undefined, right? And so what I need to represent is that at 0, I cannot define the cosecant, and so I will have what's called a vertical asymptote. And I'm going to do all the asymptotes in the same color as the graph. I'm just going to give them a dashed line so that we can see where the ones are for each particular function. Okay. Now, at pi over 4, for example, the sign is root 2 over 2, and so the cosecant, which is 1 over sine, is going to be 2 over root 2, which if we type into our calculator, Wolfram Alpha, we're going to get 1.4 approximately. So at pi over 4, we are, somewhere around here. And then, you look at pi over 6 and pi over 3, but we just kind of want a sketch of the graph and understanding of it, so we can come back to those. Let's think about pi over 2. Sine of pi over 2 is 1, so the cosecant is 1 over 1, and that is, of course, 1. Okay, moving on here to 3 pi over 4, the sign is, again, it's still positive, it's root 2 over 2, so the reciprocal of that is 2 over root 2, which again is about 1.4. And now if I move to pi, I notice that sine is now 0 again, and so I'm going to have another undefined value, and so I have an asymptote, vertical asymptote there. Okay, and if I were to keep going around my unit circle, I'd notice, look, I can define the cosecant for all of these values between pi and 2 pi, but when I get to 2 pi again, I'm going to be undefined once again. So I will have another vertical asymptote at 2 pi, and if I were moving to the left, I'd have another vertical asymptote at negative pi, right? Negative pi, it's going to be undefined again. And again at negative 2 pi. And so now we want to start thinking about, what is the graph, how will we sketch the graph in between these asymptotes? And we have a couple of points plotted here, and now let's think about what's going to happen as we get closer and closer, either towards 0 or towards pi. And if you look at the unit circle, remember we're looking at cosecant, which is 1 divided by the sine, and the sine, as we get closer and closer to 0, being the y-coordinate, the sign is going to get smaller and smaller and smaller, and so the cosecant, which is 1 over the sine, is going to get bigger and bigger and bigger because the denominator is getting smaller and smaller and smaller. So as we approach 0, we're going to be getting a bigger and bigger cosecant value. It's going to be getting closer and closer to positive infinity. The same is then true on the other side as we approach pi, right? The cosecant is 1 over the sine, or 1 over the y value, and so since the y value is getting smaller and smaller, the cosecant, or the reciprocal, is going to get bigger and bigger and bigger. And will look something like that. A couple of interesting things to note here. The first is that the minimum value is 1, and that runs like very just the opposite of what sine is, right? The biggest value that sine ever has is 1, and it's smaller everywhere else. And since cosecant is the reciprocal, things that were small, values that were small, so when sine is very small, cosecant is very big. And when sine is at its maximum, that's actually when cosecant is at its minimum. And so that's just an interesting thing to notice, and now we can sort of fill in the values in the other intervals. So thinking about between pi and 2 pi, right? Sine is negative here, and so the cosecant will also be negative, and will look just the same except going negative. And between 0 and negative pi, so between 0 and negative pi will also be negative, and then between negative pi and negative 2 pi will be positive again. And so we can sketch that out really briefly. One thing to notice is when it's negative, right, thinking about between pi and 2 pi, the biggest negative value that sine will ever have is negative 1. And so when we're taking the reciprocal, that's actually going to be the smallest negative value. So the graph over here is going to have a minimum in between these two. The smallest negative value it's going to have is negative 1, and then it's going to approach negative infinity as we move towards the asymptotes. And so there you have the graph of cosecant. Now that you have kind of the basic idea, I would encourage you to try secant and cotangent again on your own. Secant should be pretty easy now, considering that secant is 1 over cosine. And so you can kind of just march around your unit circle thinking about where that's defined, where the asymptotes might be, and what your graph will look like. So first, I think it's helpful to consider where secant is going to be undefined, and that's going to be, of course, where cosine of x is 0, right, because it's 1 over cosine. And cosine is going to be 0 at pi over 2, and it's also going to be 0 at, if you think about it, at negative pi over 2. So I can construct these asymptotes. If I wanted to continue going in the positive direction, right, it's going to be undefined at pi over 2, and then it's also going to be undefined again at 3 pi over 2. And it's really just going to, take pi chunks in between the asymptotes. And so then we can think about, what are the values in between those asymptotes. And so if you consider between, negative pi over 2 and positive pi over 2, so let's consider 0 first, right? At 0, cosine is 1, and so we'll have 1 over 1. And you might think to yourself, oh wow, this looks very, very similar to what cosecant does, and of course it's going to be very, very similar. To the point, in fact, that let's take a look at secant of pi over 4. So secant of pi over 4 is 1 over the cosine, and that's just the reciprocal of root 2 over 2, which, as we found when we were computing cosecant, is about 1.4. And so at pi over 4, the cosecant and the secant are equal, and that should make sense because sine and cosine are also equal at that point. And if we move, negative pi over 4, so I'm down here, that's again going to be 1.4. And as we get closer and closer to the asymptotes, as you might imagine, right, as we get closer and closer to pi over 2, the cosine is getting closer and closer to 0, so the secant, 1 over cosine, is going to get closer and closer to positive infinity. And similarly, as I get closer to negative pi over 2, the cosine is getting closer and closer to 0, and so the secant is getting closer and closer to positive infinity. And that will allow us to fill out the sketch of secant. Okay, so there we have it. And notice that cosecant and secant are going to intersect in a bunch of different places, right? And that's, of course, because there's places around our unit circle where we are going to have a sine and a cosine which are the same value, right? So pi over 4, they're the same. At 5 pi over 4, they're the same. And so, as we go around our unit circle, we're going to have places where the secant and cosecant are equal. Now let's look at cotangent. So cotangent is 1 over the tangent, and we can actually write this in a more simplistic way, right? So tangent of x is the sine over the cosine. So if I take the reciprocal of this, right, 1 over that, or cotangent, then taking the reciprocal of tangent is just cosine over sine. Okay, so if you want to think of it as 1 over tangent, that's fine, but really what you're doing is you're finding the cosine and dividing it by the value of the sine. And this is going to allow us to think about where the cotangent is defined and where it is undefined. Where are we going to have vertical asymptotes? And so I encourage you to now go ahead and give that a try, and we'll take a look at the result. So as you can see, cotangent is undefined. It has asymptotes in the same places that cosecant does. And that should make sense because you're dividing by sine of x for both, and when sine of x is 0, they're going to both be undefined. And so sine of x is, of course, 0 when x is 0, when x is pi, 2 pi, so on and so forth. And so the asymptotes of cotangent and cosecant are the same. And so maybe that's a good way of kind of remembering, and always being able to look at your unit circle will be helpful. So now we can think about, okay, what is cotangent going to look like in between these two asymptotes? And it might be helpful to go back and look at tangent, because remember, tangent is just sine over cosine. And so when we take the reciprocal of that, it's going to look very similar, just kind of flip-flopped. And so let's go ahead and do that. So noticing, let's kind of take a look at the first interval in between these first two asymptotes here, between 0 and pi. And so if we start moving around, and let's just kind of look at pi over 4. So at pi over 4, sine and cosine are the same, and so cosine over sine is going to be 1. And so at pi over 4, we can plot a point at 1. And at pi over 2, if we keep going, pi over 2, cosine is 0. So the numerator is 0, and the denominator is 1, meaning that tangent, or cotangent rather, will be at 0. And as we keep going around, considering 3 pi over 4 in between pi over 2 and pi, the cosine is negative and sine is positive, so it's going to be negative 1. And now we have a couple of points, and we can sort of think about, okay, what's going to happen as we get closer and closer to this asymptote of 0. And as we get closer and closer to 0, notice that cosine is getting closer to 1 and sine is getting closer to 0, meaning that the denominator is going to be getting very, very small and the numerator is going to be getting very close to positive 1. So we're going to approach values that are very close to positive infinity. And as we get closer and closer to pi, notice that cosine is getting closer to negative 1 while sine is getting closer to 0 from the positive side, and so we're going to have something close to negative 1 over a very, very small positive number, which is going to be a very big negative number, so closer to negative infinity. And so there we have in this particular interval, and you can actually do the same thing for all the other intervals, and you'll see that it's just the exact same graph, just like tangent is. In each interval, it's going to look exactly the same, and you can go through and think about why that is, looking at specific values of cotangent. Alright, and there you have the completed graph of cotangent along with secant and cosecant. Okay, so it's now time for us to look at inverse trig functions. So we've looked at inverses before, and now we're going to apply the same ideas and principles that we've discussed in looking at trig functions. So let's consider sine of x. And if we want to find the inverse of sine of x, we're going to have an equation, y equals the sine of x. And let's just think about what this equation does. So the domain are all the values of x, all the different angles that you could have along your unit circle. And when you take the sine of it, what you're returning, the sine is saying what is the y coordinate of the point where the terminal side of this angle intersects the unit circle. And if we want to have an inverse function, then we're going to want to have a function which returns to us the x value. And so let's think about what this x value really is. This is a part of the domain, and the domain are the angles, right, or the radian measures. And what we want is a function that will take as an input the y coordinate, which in this case is our output, and will tell us the angle that has a y coordinate of that value, or as it is defined, right, the y coordinate is the sine. So what we're looking for is a function that will tell us the angle whose sine is whatever this value is. And I'm literally going to write that in there because that is the exact meaning. Okay, so think about what we have here. We have some function which is going to answer the question, the angle is going to tell us the angle whose sine is y. And that is going to be equal to x. And that's exactly what we want because the sine of x is equal to y. And so this function, what we call this function is we call this the inverse sine function. And there are two ways that it is written. Okay? So the technical mathematical term is that it is the arc sine function. Okay? The arc sine function. And I'll write this above here. So I would want to find the arc sine of y, okay, and that is literally finding the angle whose sine is y. That is what arc sine means. And another way of writing it is the inverse sine, which is written as sine with a -1 power, okay, as such, okay. And so what we've done is we've written the inverse function, a function that will take in the output, whatever the sine value was, and will return to us the angle whose sine is that value. And so now, of course, we have a function where the input are the y values, and we always make that switch, right, where we want the input to be the x variable, right? So f inverse of x, there are two ways to write this. The first is arc sine of x, or we could write it, put the or here, or we could write it as sine, the inverse sine of x. And it is important to remember that this is not an exponent. Okay? This is not an exponent. You may need to make a note for yourself. This is the inverse. And so that's why sometimes we write it as arc sine, because that way no one's getting confused whether you're raising this to the -1 power or not. Okay? And so I want us to be very clear what it means when we see arc sine or inverse sine. Okay? What we are saying is if you take the arc sine of a value, you are saying find the angle whose sine is this value. If you take the inverse sine of a value x, you are finding the angle whose sine is this value. And so that's important, and we want to make sure we have that captured. So we're actually going to write that down below so that we never forget it. Okay, and there you have it. So the function, the arc sine function, arc sine of x, or what we call inverse sine of x, is saying find the angle whose sine is this value, x. And so now we want to think about what will the graph of the inverse sine look like. And thinking back to our work with inverses so far, you'll remember that for any function, to graph the inverse, we reflect over the line y equals x. And so let's go ahead and sketch out with kind of a dashed line what the line y equals x looks like so that we can think about what the reflection will look like. So let's take a look at what the reflection will be. So starting at 0, notice that at 0 the sine curve and the line y equals x are in the same spot. So this point will remain in the same place, and it looks as though the sine curve is basically on the line y equals x for the first few positive points. And so the reflection will also be on the line y equals x. But as the sine curve starts to move away, so will the reflection. And so I'm just kind of going to show us where some of these points are going to look to end up. And the point here where the sine curve intersects the x-axis at pi, it's going to intersect the y-axis. The reflection is going to intersect the y-axis at pi. And so you can see, and I'm going to sketch out kind of what the reflection will look like for its first few points. And then, of course, as I continue on, so this point here, when it's reflected, will be on the other side of the y-axis. And so we can see that we're just going to have this same sine curve, but in a kind of a vertical fashion. And the same is true as we look at the negative values, right? It seems to be lining up perfectly, and then it will start to curve away. It will intersect the y-axis at negative pi, negative 3.14, so on and so forth, and then curve back down. Now, this should make sense in thinking about the domain and range of the original function, the sine function, and then noticing that for our inverse, the range of the original function will be our domain. And so if we were to look at the range of our original function f of x, we know that the range, look, the sine function has a maximum y value of 1 and a minimum y value of -1. So the range is going to go between -1 and +1. And so it should make sense now that the domain of our inverse function is going to go between -1 and +1. And we can see that now as we look at this sine curve that's been now kind of turned on its head. The biggest value in the domain, input value, will be a +1, and the smallest value will be a -1. Now, I purposely haven't sketched it out yet because there's something that we need to realize, and that is that the way we have this reflection sketched out, it would not be a function. It wouldn't pass the vertical line test. And this should make sense, and here's why. Imagine that we have some value like 1/2, Okay, so we want to know what is the arc sine of 1/2. In other words, what is the angle whose sine is 1/2? And if you look at your unit circle, you might say at first, okay, well, at pi over 6. But that's not the only angle, that's not the only radian measure which will have a sine of 1/2. There's going to be 5 pi over 6, and then you can rotate more than one time around, more than 2 times around. In fact, there's infinitely many different angles whose sine is 1/2. And so that's why my sine curve, as it rotates kind of and circles back around, is going to have all these different possible outputs. And so what we want to do is we want to limit ourselves to just the ones that matter, so that we have all of them, but that they don't repeat. Okay, and so we want to think about where are we going to have to restrict ourselves as far as how far, what is our range going to have to be, so that we are only hitting each value once. And to do this, we're going to use our domain. So what we're going to do is we're going to think about, okay, if we go from -1 out to +1, and we restrict ourselves to only the first angle whose sine is that value, what will the curve look like? Okay, and so if I can try here, this is about +1 and about -1. And so now we're taking a look at our reflection. Notice that we're going to stay pretty much on the line y equals x, and then it is going to slowly move away. Okay, and that's where we're going to stop. Okay, and then the same thing is true going towards -1. We're going to go pretty close to the line y equals x, and then we're going to slowly branch away, and then we're going to stop. And there we have in green the graph of the arc sine, or the inverse sine of x, the angle whose sine is. And let's think about what this range is going to be. So if I input an x value of 1, the angle whose sine is 1, and we think about, where is this going? Where is that first appearing? And we can think about is that this is pi over 2, right? Okay, so this value should be pi over 2. We're a little. It looks like we're a little above, but that's okay. The purpose is to understand that we're going. The biggest y value that we're going to have is pi over 2, because that's the angle whose sine is 1. And similarly, what's the angle whose sine is -1? That would be negative pi over 2. Okay? So our range is going to go between negative pi over 2 and positive pi over 2. We should actually make these square brackets, right, because we will actually reach those two values. Okay, so that is the inverse sine. I'm going to go in slightly less detail over the arc sine, the arc cosine slash the inverse cosine function, and then also the inverse tangent function. But the same ideas are going to apply. Okay, so now we have cosine of x, and the inverse of cosine is what we call arc cosine, or inverse cosine. And this function, the arc cosine of x, or the inverse cosine of x, either way you want to write it, what this means is the angle, what you're finding is the angle whose cosine is x. So, for example, if you had 1/2 as your argument again, the angle whose cosine is 1/2, and if you think about that, you're going to, pi over 3, that would be the value that you'd come up with, right? And here, we're going to kind of look at some of the same things we looked at for sine and inverse sine. And first, I want to think about what will the domain of our inverse function be. And so to figure that out, we're going to look at the range of our original function. And the range, of course, for cosine, right, from +1 to -1. And so our domain, similarly to inverse cosine, for inverse cosine, for inverse sine, we also had from -1 to +1. And for inverse cosine, we're going to again have that same domain. And so we can think about, we're going to be going from, positive 1 to negative 1, and if, maybe positive 1's over here and negative 1's over here. So just to keep that in mind. And then we're going to think about the range as well once we actually make that reflection. So now let's think about what this reflection is going to look like. Let's start at 0, and let's think about the point that we have when x is 0. So this point here on cosine of x will reflect over to the x-axis, so I'll have a point here, and then these points will reflect, and eventually we'll get to this point, which is right in the center, and that point is actually not going to go anywhere because it's on the line y equals x. And so if you can imagine, we're going to have sort of a semi-curve here, and then as we continue moving on, right, we continue reflecting over, and eventually this point here is going to reflect over and actually hit the y-axis. So you can consider us, starting here and moving over and hitting the y-axis here. Okay? And as we continue on, let's just think about where will this point end up. Right? And so we can kind of imagine ourselves, and this is where we have pi, right? So this is reflecting over here, right? Pi units in the y direction. And so we can kind of picture our function moving like that, okay? And so let's go ahead and actually sketch that out, and what we'll notice is that there we've gotten all of our domain taken care of, right? From negative 1 to positive 1. Because here this is negative 1, and so when this reflects over, this will be negative 1 units to the left, and this point over here is at positive 1, and so when we reflect this over, we'll be at positive 1 units to the right. And so there we have our graph of the inverse sine. And so what we can notice here is that between negative 1, maybe mark that, between negative 1 and positive 1, we can see that the range of our values, the range of the outputs, go from 0. And what is this value up here? Well, notice we got this point here by reflecting from the point that came with an x value on the x-axis of pi. And so this is going to go from 0 to pi. And if you look at your unit circle, you'll notice that you get all the possible values of cosine if you go between the angles of 0 and pi, right? You're going to get all the positive values and you're going to get all the negative values. And so our range is between 0 and pi. And now what we want to do, really briefly, is I kind of want us to think about why this graph makes sense in terms of our definition. In other words, the angle whose cosine is. And so let's imagine that our input value was 0. So we had arc cosine of 0, meaning we're looking for the angle whose cosine is 0. Well, if you look at your unit circle and you think about what is that angle going to be, you would see that you would end up at pi over 2, right? So you'd return pi over 2. And then, maybe let's find the angle whose cosine is negative 1. Well, you would go to pi radians, right? So your range is going to be in between 0 and pi radians, right? Imagine you wanted to find the inverse cosine of 1, meaning you want to find the angle whose cosine is 1. Well, that is 0, right? So you go all the way from 0 up to pi. All right, now let's take a look at inverse tangent. All right, let's take a look now at inverse tangent. And to help us kind of understand what inverse tangent is doing, it's helpful to look at tangent of x. And we remember, since we just graphed this a few minutes ago, that tangent of x has some vertical asymptotes because you can't define the tangent at pi over 2, 3 pi over 2, negative pi over 2, so on and so forth. Any place where our terminal ray is going to be perfectly vertical will have an undefined tangent. And so that creates this kind of funky looking graph, and you can imagine that when we reflect this graph over the line y equals x, right, we're going to have something that looks really kind of crazy, and we'll have all these overlapping sort of swale-like designs. And you can already sort of picture in your mind, right, that this is going to be is not going to be a function. The inverse tangent won't be a function unless we restrict it like we have for inverse sine and inverse cosine. So with that kind of looming in the forefront, let's now look at what inverse tangent means. And of course, there's two different ways to write it. We can write it as arc tangent of x or inverse tangent of x, and both of these mean the same thing. So they're the inverse of tangent, meaning that when we apply them to some value, we're trying to find the angle whose tangent is whatever that value happens to be. So just as an example, let's find the arc tangent or inverse tangent of negative, let's do positive 1. And if I'm looking at my unit circle, right, I'm trying to find the angle whose tangent is 1 in this case. And this is pretty simple, right? We're looking for a terminal ray where the slope of that ray is 1, in other words, where the sine and the cosine are equivalent, and that happens at pi over 4. Okay, and so that should make sense, and that can kind of help us get a grasp on, maybe just one point that we would plot for our inverse tangent function, right? When the input is 1, the output will be pi over 4. And you could go to a couple more examples if you want to, but let's now start to think about what the inverse tangents graph is going to look like. And to help us get a grasp on that, let's remember that for any inverse function, the domain of that function is going to be the range of the original function. So for tangent of x, it's pretty obvious that we can have any value between negative infinity and positive infinity, right? Because you're going to be able to get as close to a perfectly vertical line, either in the upward or downward direction, and so you'll be able to get any slope you want between negative infinity and positive infinity, which means that the domain of inverse tangent is going to be anything from negative infinity to positive infinity, meaning that for any value between these two, I can find an angle that has a tangent for that value. All right, and that should make sense. All right, so now let's think about what the graph is going to look like. And to do that, let's consider what would happen if you were to reflect all of these different pieces of tangent over the line y equals x. And if you were to do that, as we talked about at the beginning of our discussion of tangent, we'd have all these overlapping pieces. So it would fail the vertical line test. And that should make sense, again, because there's not just one angle that has, for example, that has a tangent of 1. Right? Pi over 4 has a tangent of 1, but so too does one full rotation plus another pi over 4, right? And so too does 2 rotations around my unit circle plus another pi over 4. So there's infinitely many angles which could give us the same tangent. And because of that, for the input of 1, we'd have many different outputs. And of course that makes our function not a function. It would make it not a function. And so we need to restrict ourselves to a portion of the graph where we'll get all the values of tangent, but we'll only get them one time. So to help us with this, let's look at our unit circle, and let's consider what part of the unit circle do I have to look at in order to make sure I get all the possible values of tangent. So consider first the first quadrant. In the first quadrant, I have all the possible positive values of tangent, right? Any possible slope you could imagine from 0 to positive infinity can be found between 0 and pi over 2. And similarly, all the negative values of tangent can be found between 0 and negative pi over 2. And this correlates perfectly to this middle interval for tangent, right? This middle interval for tangent has everything from negative pi over 2 to positive pi over 2. And so if we forget about all the other pieces of tangent and only reflect the interval between negative pi over 2 and positive pi over 2, that will still give us all the values of tangent that you could possibly have, except you'll only get them one time. And so we won't have to worry about having an inverse function, which in fact is not a function. So we'll kind of forget about these, and I'm going to block them out in just a second, and we're going to only reflect this middle portion. Okay, so you can see that I have gotten rid of the sort of extraneous pieces of tangent of x and limited ourselves to the pieces of the part of tangent x between negative pi over 2 and positive pi over 2, because as we discussed, that incorporates all the possible values of tangent that we could ever have, And so by limiting ourselves to that, we will end up with an actual function when we reflect over the line y equals x. Now, to help us understand what the reflection will look like, there's a couple of different kind of moves we can make. The first is just to sort of look at our tangent function and think about what will happen to some of these points as they reflect over the line y equals x. But what I encourage you to think about is also that the asymptotes are going to reflect over the line y equals x. And what this will do is it will change the asymptote that is vertical, that goes through the line, goes through x equals negative pi over 2, and it will now go through y at negative pi over 2. Okay? And this will allow us to sort of construct our asymptotes in the same place except going horizontally. And of course, if you don't want to look at it that way, you can also just think about, okay, what will happen to each of these points as we reflect over. And we can see near the origin, it's pretty much on the line y equals x. But as we move further on to the right and to the left, and the function gets further and further away from the line y equals x, and when we can reflect these over and see what the function will look like. So I encourage you to try this on your own first, and when you come back, I will have it graphed out for you. Okay, so here we have the reflected function, the inverse function, or the arctangent of x. And notice that it's not only has the blue function been reflected over the line y equals x, but also the asymptotes have reflected. And so an interesting thing to notice is that when you reflect a vertical asymptote over the line y equals x, it is now a horizontal asymptote. And so we have horizontal asymptotes that are at the line, that are the line y equals positive pi over 2 and negative pi over 2. So that's an important thing to notice here, that this is positive pi over 2 and this is negative pi over 2. And it should make sense that we will never get an output from inverse tangent that is actually pi over 2 or actually negative pi over 2. Because notice that the inverse tangent asks the question, what is the angle whose tangent is that value, or x? And in order to have an answer come back with pi over 2 or negative pi over 2, you would have to have a tangent that is infinite, right? Undefined. And so that is just not going to happen, right? You're never going to be able to actually input a value that is undefinable because you can't define it. It'd be a contradiction. So we're going to get very close to values of pi over 2 and negative pi over 2, but you'll never quite get there. Further, we can see a couple of points that should make sense, right? So we talked about arctangent of 1, and so 1 is going to be a little less than pi over 2, right? Maybe about here. And we know that an arctan of 1 gives us an output of pi over 4, right? Because the angle whose tangent is 1 is pi over 4. And so you can see that the point 1, when x is 1, we should get an output of around pi over 4, which should be less than 1, about 0.75. And you can see that that makes sense there. Similarly on the negative side. So the range of our inverse function is going to go between negative pi over 2 and positive pi over 2. And it should have rounded brackets because, as we talked about, these are asymptotes. We'll never actually get an output of positive or negative pi over 2. And so there you have arctangent or inverse tangent. We're going to take a look at a couple of problems for you to consider, just working with arctangent, arc cosine, arc sine, and getting kind of familiar with inverse functions. Okay, most of these are pretty straightforward. The last one is a little tricky, and I want to talk about how you should think about this. So remember, we want to work inside first, so don't worry about cosine yet. Let's worry about how to find the arctan of 2 over 3, meaning, what is the angle whose tangent is 2 over 3? Now, if you look at your unit circle, and you're thinking about it, and I'm just going to draw a circle here, we know that this angle is somewhere in the first quadrant, right? How do we know that? Because the tangent is positive, right? And so the slope of the terminal side must be positive. But none of the angles that we know, none of our special angles, pi over 6, pi over 4, pi over 3, has a tangent whose value is 2 over 3. And so what we need to do is construct ourselves our own right triangle here, okay? Because the tangent is the rise over the run of this terminal side. And so we know that the rise is 2 and the run is 3, and so we can construct ourselves this angle. Notice that the radius is not going to be 1 for this if we were to draw a circle that went all the way around, right? And so what we need to do is think about what will the sine, or in this case the cosine, of this angle be. And so in order to find the hypotenuse, we'll use the Pythagorean theorem. 3 squared plus 2 squared is equal to the hypotenuse squared. And 3 squared is 9, 2 squared is 4. Add them together, you get 13. Take the square root, you get square root of 13 as your hypotenuse. And so now you know for this angle, the cosine is adjacent over the hypotenuse, and the adjacent is the value 3, hypotenuse is root 13, and so our cosine of this angle is 3 over root 13. So if ever we have a value of an inverse tangent, inverse cosine, inverse sine, where we don't have a particular angle on our unit circle that fits that bill, we can create the portion, or we can create the right triangle that it comes from using the information that we're given. And so that's a good strategy to have in your back pocket if you ever are not able to use the values on your unit circle. So this should bring back fond memories of the last unit of the year, constructing sinusoidal functions to model real-world phenomena. So one of the most easy things to model are things that rotate in a circle, because they will repeat values over and over again, and so they fit the bill of a periodic function. So thinking about a Ferris wheel where you're going in circles, your height above the ground is going to repeat values. And so we want to model this using a periodic function. And since we're told a bunch of information, we're able to fill out the entire function and create all the parameters. So our amplitude will be 28, our midline will be 32, we have a period of 4 minutes, which means the b value must be pi over 2. And we're going to use a cosine function because we want this our height above the ground, to start at its maximum, and a cosine function with no phase shift will have a y-intercept at the maximum value. I would recommend that if this was something that was a little confusing, go back to the latter parts of Unit 6, check that out, check some of those videos out, and also take a look at the solutions to the final task, which is also posted in the Algebra 2 video section. So that would be some good review if you are in any way a little confused by creating sinusoidal functions. Alright, so our goal is to better understand the different types of transformations that we can make to sine and cosine functions, sinusoidal functions. And obviously we want to understand these so that we can better model real-world situations, just like we did with the Ferris wheel. So looking at all the different parameters, meaning the different things that we can do to our sine function, so we can multiply it by a coefficient out front. It's our a parameter, often associated with the amplitude. Inside of the argument of sine and cosine, we could multiply whatever the argument x is by some value b. We could also subtract, or if you made h negative, add some value to x. And then overall, you could add something to the first part of our function. That's a k value, often associated with midline. So what I would recommend you doing is, off the top of your head, just kind of writing down what a changes to the parameters a, b, h, and k will do to your function, and use mathematically precise language as much as possible. So transformations, translations, stretching, shifting, things like that. And then we'll come back, we'll take a quick look, talk about a couple of them, and in the assignment I will give you some to practice. Alright, let's look first at the value of a. So as I multiply, if a were greater than 1, right, as I multiply something by bigger and bigger values, that will stretch my function, right? So remember, sine and cosine have a max and min value of 1 and negative 1. So if a were 3, for example, all of a sudden my max and min would now be 3 and negative 3. So it would be stretching my function either stretching it out vertically or kind of squeezing it in vertically, right? If a were like 1/2, all of a sudden the max and min would be half and negative a half. So a, we can say, stretches our function, and also the absolute value of a is our amplitude. All right, so there you have it. I also included the fact that if a is negative, just like multiplying anything by a negative, we'll change the sign, and so a negative value of a will reflect over the midline, a function of the midline. All right, let's go down to k first. So changing the value of k is very, very straightforward, right? If I add or subtract something, I'm either going to shift it up or down, and the mathematical terminology for that is translate. So k, also known as the value of the midline, so the midline is going to be the line y equals k, and it will translate our function up or down. All right, now let's go to the b coefficient. And I'm going to go over b and k coefficients, those parameters, fairly quickly. If you want a more in-depth analysis, go ahead and go back to the Unit 6 videos, or just maybe post a question on the discussion board asking for a little more clarification. Or you can go and kind of try and think about it yourself and maybe pull out your unit circle. But I'm going to go over these kind of quickly. Let's think about the b coefficient. So imagine that your h value was 0, just for a second, and so you had b times x in your argument, and imagine that your b value now was 2. So you had, say, cosine of 2x. What multiplying your x value by 2 will do is it will move you farther along your unit circle than you would have if it were just a 1. So imagine your x value was pi over 4. Well, when you multiply that by 2, you're going to go to now pi over 2, right? So you're going to be moving around your unit circle faster. In other words, your period is going to decrease, right? So the bigger your b value, the smaller your period, and what that means is that your maximum values and your minimum values are going to be closer together. So this compresses your function or stretches it out, either stretches it horizontally or compresses it horizontally. Think of a slinky, for example. So if your b value is less than 1, it will stretch out your function horizontally. If it is greater than 1, it will compress it horizontally. Okay, so there's b. And I want to talk about the couple of relationships that we have. So the period is 2 pi divided by the absolute value of b. And we have that absolute value there. There's a chance that you could see a b value that's negative. There's really no reason to. But if you did, you wouldn't want a period that's negative, right? It'd be impossible for there to be a negative distance between two maximum or minimum points. And so you're always going to want to think of the period as a positive value. And so you can also calculate the value of the absolute value of b. And of course, you're normally going to just make b positive, so it won't really matter. And that's going to be 2 pi over the period. So if you have the period and you're looking for your parameter b, you can find it, and if you have your b value and you're looking for your period, you can also find it. Now let's think about the h value, and to do that, imagine that your b value is 1, so you just had x minus h, and consider h as a value of pi over 2. So you'd have, say, for example, cosine of x minus pi over 2. So if you were to plug in 0 for x, instead of beginning at an angle of 0 radians, you'd be beginning at 0 minus pi over 2, or negative pi over 2 radians. So if you're looking at your unit circle, you can imagine that having a positive h value will kind of make you start at an earlier place, kind of wind your clock back, if you will. And so what that does is it shifts your function to the right, because now all of a sudden, in order for you to have the value that you would normally have at cosine when x is 0, now that you have x minus pi over 2, you need an x value of pi over 2 in order to get cosine of 0. So you have to move to the right pi over 2 units to get that point that you normally would have at your y-intercept. And so what this does is controls the phase shift. So a positive h value phase shifts to the right, and a negative h value, and of course you can think about what that means. If you had negative times a negative, it would show up as positive. A negative h value will shift your function to the left. And we always want to use correct mathematical terminology, so you can think of it as a shift, but the correct mathematical terminology in terms of transformations would be a translation. So the h value will either translate our function to the left or to the right. So there we have it. I've also marked the sign that h should have if you're going to translate left or right. Again, if you want some little more detail here, go ahead and take a look at the Unit 6 videos. If not, go ahead and tackle the assignments and post any questions that you have on the discussion board.